Imagine you are seeing this reasoning test for the very first time. On the left, you have a question matrix comprising a 3x3 grid of panels with a missing 9th panel. And on the right, you have 8 panels as your possible answer options. Now, perhaps you may not know that this is called a Raven's progressive matrix, but you could certainly look at it and figure out the correct answer. Now, to get machines to do abstract reasoning and solve RPMs, we shall introduce what we call algebraic machine reasoning. The idea is that novel problem solving is reduced to routine algebraic computations. Here by novel, we mean that we can solve RPMs without having seen RPMs before. By algebraic, we mean computative algebra and computational algebra, but not linear algebra. Instead, we use algebraic notions such as ideals and primary decompositions. Effectively, reasoning becomes computing the primary decompositions of ideals. With our new reasoning approach, we have surpassed human-level performance for solving RPMs. On IEEE dataset, we achieve an accuracy of 93.2%, better than human accuracy at 84.4%, and much better than the previous state-of-the-art. How do you achieve this 16.6% improvement over state-of-the-art? How do we reduce reasoning to algebraic computation? Hi, my name is Ernest Strong, and I'm very excited to introduce to you algebraic machine reasoning. For more details, check out our paper linked in the description. Let's begin by explaining what ideals are. Suppose we have n variables, x1 up to xn. We can form polynomials in these n variables. We can add and multiply polynomials. Now take all polynomials together with plus and times. We get an algebraic structure called a ring. The ring includes monomials, polynomials with one term and coefficient 1. A subset of a ring is called an ideal if it has this form, given in terms of some polynomials. For example, suppose our ring has two variables x1, x2, and say g1 is x1 squared and g2 is x2 cubed. Then we can define this ideal I from g1 to g2, consisting of all polynomials whose terms look like this, where the exponent for x1 is at least 2, and the exponent for x2 is at least 3. Intuitively, g1 and g2 are generators of this ideal I. Putting all the gi's together, we get what is called a generating set for our ideal I. So to initialize an ideal, we can specify its generating set. Once we have a few ideals, we can add, multiply, and intersect them. Now, every ideal has infinitely many generating sets, and it is possible for two seemingly different generating sets to describe the exact same ideal. A monomial ideal is a special kind of ideal that has a generating set consisting only of monomials. And with that, we define a concept to be a monomial ideal of our initialized ring. Let's see some examples of concepts. Suppose we have 4 variables. We can construct concepts generated by a single variable. These are called primitive concepts. So with 4 variables, we have 4 primitive concepts. We can impose meanings to these primitive concepts. For example, our first primitive concept could mean red. We can also construct other concepts in this red concept. How we interpret the concepts depends on what meanings we give them. But concepts could have non-obvious meanings because they have more generators. For example, this ideal J here looks complicated. Yet we can decompose J as an intersection of these two ideals. Intuitively, these two new ideals are simpler than the original concept J. There are multiple good reasons why we define concepts as ideals. First of all, we want to capture the expressiveness of human reasoning. For humans, we can generate infinitely many concepts from finitely many primitive concepts. Algebraically, this is made possible because of the richer structure of ideals that allows for more operations beyond those from set theory. Also, in contrast to logic-based reasoning, we do not assign truth values or any numerical values to variables. This means we can reason with concepts that do not naturally have associated numerical values. Defining concepts as ideals is also compatible with concept theory in cognitive science. For human cognition, we now understand that the compositional structure of concepts is important for learning new concepts. Algebraically, we have this structure where concepts can be decomposed as intersections of concepts. There's also a cognitive theory on the essence of concepts. This means we describe concepts in terms of its features, although we should be careful to distinguish defining features from irrelevant features. This is analogous to computing a minimal generating set of an ideal, where we get rid of irrelevant generators. And finally, humans can reason with concepts that are partial definitions. Algebraically, we can do that too. So overall, defining concepts as ideals is reasonable. Another useful idea from cognitive science is that semantically similar concepts are naturally grouped to form a more general concept. For example, concepts such as red, green, blue, and yellow can be grouped to form a new concept representing color. Hence, we can construct what we call an attribute concept. This is formed by combining multiple primitive concepts, which themselves can be regarded as attribute values. Going back to our RPM task, we need to identify relevant attribute concepts, which are number, position, type, color, and size. Once we have our attribute concepts, a concept shall be deemed meaningful to us if it is contained in some attribute concept. For example, let's consider these two concepts. The first concept is generated by red, green, and blue. The second concept is generated by red, square, and large. Intuitively, the first concept is more meaningful since it is contained in the attribute concept color. In contrast, for red, square, and large, They're not quite attribute values of some common attribute. Next, let's talk about primary decompositions. The idea is that every ideal has a decomposition as an intersection of finally many primary ideals. The entire intersection is called a primary decomposition, and the constituent primary ideals are called the primary components of this primary decomposition. When J is a monomial ideal, meaning that J is a concept, then there is a unique minimal primary decomposition that we can compute. How do we reason with primary decompositions? Let's begin with K concepts, J1 to Jk. A common pattern of these K concepts is itself a concept containing those K concepts. If there are several common patterns, say K1 to Kr, then each of our original concept Ji can be expressed as having an intersection of the common patterns together with a leftover ideal representing what's different. Algebraically, our goal is to compute the common components K1 to Kr. To do so, we first compute the primary decompositions of our original concepts, then extract the common primary components. After this extraction, the intersection of the common primary components would form a new concept which can be regarded as a common pattern of our original concepts. Putting all our algebraic ingredients together, we have our algebraic machine reasoning framework for storing RPMs. There are two stages in our framework. The first stage is perception. Here we use the usual object detection models to collect the raw perceptual attribute values for each entity in the panel. Each entity is then encoded as a monomial, which then becomes a generator for the concept representing the panel that this entity belongs to. The second stage is reasoning. This is where we use algebraic machine reasoning. Here we extract patterns from the RPMs via 4 invariance modules. Intuitively, the 4 modules check for 4 general types of invariances across an input sequence of concepts. The checking involves computing the primary decompositions of the concepts in our sequence and solving ideal-based problems. Because our reasoning process involves extracting actual RPM patterns, our framework is able to directly generate answers just from the question matrix, and we achieve an average similarity score of 67.7% for answer generation. When we look at the failure cases, other than ambiguous RPMs with accidental multiple correct answers, we found that our framework would discover unexpected new patterns. For example, here's a new discovered pattern. With this new pattern, our framework concludes correctly that both B and H are equally valid answers for this RPM. Now, the discovery of new unexpected patterns is our strongest evidence that this idea of reasoning by computing primary decompositions is generalizable. Could we use the same algebraic approach for other reasoning tasks? This notion of primary decompositions comes from commutative algebra. Effectively, we have established a completely new connection between machine reasoning and commutative algebra. There are many deep algebraic results and lots of algebraic operations on ideals we have not yet tapped on. Can we use them to extend reasoning capabilities? Finally, if you're interested in both algebra and AI, do consider joining our team. You can reach me directly via email. Thank you for watching. I hope you like this new algebraic way of thinking about machine reasoning. Join us. Join us in exploring the possibilities of algebraic machine reasoning.